All right, so in this video, I want to prove that the limit as x approaches zero of sine x over x is, sorry, not zero, but one. See, let's go ahead and correct that before we go any further. Prove that the limit is equal to one. All right, now the first thing to keep in mind, drink a little tea here. But the first thing to keep in mind is that, if we can't solve this limit by just substituting in zero for for x, because of course it blows up if you do that. So, um, so we're going to do what's called the squeeze theorem. Okay, so we'll write that there and we'll get back to it. But before we get into all the details of the squeeze theorem, the easy way to determine that the limit as sine x over x approaches zero is one is by taking a look at this. So let's think about this. Let's say you have an XY plot. So sine looks something like this. So sine comes up through the origin and does like this. So this obviously is not perfect, but you get the idea. Now, the line y equals x looks something like this. Now, this in theory will be kind of like a straight line on the sine curve, So just try to use your imagination. And let me just go ahead and redraw that part so that it can be more accurate. All right, so it comes through. It looks kind of like that there, okay? All right. So think about this. Say, for example, you were to zoom in to this area of this graph here. If you were to zoom in really, really tiny, what you would see is, let's say we zoomed in really tight right there around the origin. You would have that little line from sine x, and then you would also have on top of it, right on top of it, you would have y equals x. Now, what I'm trying to illustrate to you is the fact that if you put in really, really small values right around x equals zero, then sine x and x look the same, which means essentially that for values getting right up there close to x equals zero, sine x over x, sine x divided by x, like I said, not at zero, but close to zero, sine x over x does actually become one because you figure it's about the same up top and at the bottom. Okay. So that's one way to see it. That's like the easy way to see it. And that's kind of like the whole essence of calculus. Using really small values and really kind of like getting really close, really detailed. So now let's actually prove that this limit is equal to one according to the squeeze theorem. Let's go ahead and erase this stuff here. All right. So what we're going to do is we're going to draw a unit circle. And we are going to, okay, there's your unit circle there. All right, let's see. So, and then we're going to draw, I want to do a different color here. So let's undo that. Let's do red again. So we're going to draw this right here. Just a radius. The angle is going to be X, okay? Now, so if we were to look at this here, the sine of angle X is going to be the opposite side over the adjacent side. But because the opposite side, because the adjacent side is this radius, the radius of a unit circle is 1. So it's just sine is just going to be equal to sine of X is going to be equal to Y. So this Y, this opposite side Y is going to be sine X. And the same deal goes for the cosine of X. It's going to be this X side over the hypotenuse. So in other words, cosine of X is just going to be cosine of X. So that's cosine X there. Okay. All right. Now, what we're going to do now, so keep that in mind. The second thing I want to do is to let's see. Let's extend this out to here. And we're going to draw a straight line from this edge of the circle. So here now, this length right here is 1. Let me see. Yeah, this is 1. And this line right here, what does that measure? So if you look at this, the angle that we're dealing with is still X. But what is this measuring? Now, the thing to keep in mind is that remember that tangent of X is equal to sine, sine X over cosine X. In this case, we draw this line out here. This is sine, this is cosine, but now this adjacent side cosine is going to be equal to 1. Okay. So, and I guess I should rephrase this as, let's say it this way. It's the opposite side over the adjacent side. So the opposite side is going to be just the opposite side. And then the adjacent side we know is going to be 1 because this now, the side of this triangle is 1. So that means this opposite side, if you look here, is just going to be tangent X. Okay. And we are going somewhere. Okay. So check this out. So if we were trying to find, I'm going to do one more color here. Say, for example, we're trying to find the area of this internal slice of pizza, so to speak, inside the circle here. If we're trying to find the area of this circle here, how would we do that? So the area of this circle right here, this little slice of pizza here, remember it includes that arc. The area of a circle in general is going to be pi radius squared. The radius is 1, so it's going to be pi 1 squared, or in other words, so I just say pi radius squared. And then because it's only that piece of this whole circumference, then we want to use something to like a proportion type of calculation to take that into account. So the proportion of this circle that's represented by this sliver is going to be X degrees out of 2 pi degrees. So you're going to multiply this times X over 2 pi, because that represents the proportion of the circle that encompasses this pizza slice. So if you were to simplify that, this will be the pi's cancel. So you basically have X over 2. Now, the thing to note with this area is that this area of this pizza slice lies between the area of this first red triangle that we had and the area of the blue triangle. It lies right in between. So watch this. And I'd write it in the different colors. So the area of it, so remember the area of a triangle And remember, we're proving this geometrically. So that's why it's like, why in the world are we doing this? It seems random, but you'll see what I mean soon. All right. So the area of this triangle right here, the area of a triangle, let me put it that way, is the area of a triangle is 1/2 base times height. So keep that in mind. The area of the the red triangle is going to be 1/2. The base is cosine, and then the height is sine. So 1/2 cosine x sine x. So this is less than, excuse me. So this is less than, now let's do the area of the pizza slice. We said that's x over 2. And that is going to be less than the area of the blue triangle, which is going to be 1/2 and then tangent over 1. So that's just 1/2 tangent x. Okay. Now, we're just going to keep on going. You'll see where we're getting here. So you can take a 1/2 out of all these. Since a 1/2 is present in all these, this whole thing can be divided by 1/2. So you can get rid of that. So that becomes, and I'm just going to use black now, cosine x sine x less than x, which is less than tangent x. Now, let's put that tangent in terms of sine and cosine. So cosine x sine x is less than x is less than sine x over cosine x. Okay. So now what we're going to do, if you notice, this has a sine in it and this has a sine in it. So we can divide everything by sine. And what happens is sine will go away on these two ends, but then sine will be underneath here. So this becomes cosine x is less than x over sine x is less than, and we divide it by cosine, so that's 1 over cosine x. Okay. Now, finally, what we can do is, remember, this is what we're wanting to prove right here. So finally, what we can do is we can flip these, and when we flip these, then the inequalities switch their direction. So this becomes 1 over cosine x is greater than sine x over x, which is greater than 1 over cosine x. I mean, not 1 over cosine x, but cosine x. I'm sorry, we flipped everything. And we're almost done here. All right. So now, remember, what we're doing is we are wanting to find the limit as x approaches 0 for this function. So what we're going to do is we're going to go ahead and plug 0 into these two parts here. And if you do that, the cosine at 0 is equal to 1. So that becomes 1 down over here, and sine x over x, and then 1 right there. So take a look at that. So basically what we're saying is sine x is between 1 and 1. So if you're between 1 and 1, then basically, if that means that if the limit of those two end functions is 1, then the limit for sine x over x also has to be equal to 1. So this right here essentially proves that the limit is 1. Now I'll finish off by just stating what the squeeze theorem says, and then we'll call it a day. It basically is we've basically illustrated it here. Make sure if you need those notes that you go back and look at them. All we did was prove stuff. So after it's proven, you really won't need to necessarily prove this again, I believe. All right. So The squeeze theorem basically says this. It says if you have a function, so if you have this type of situation, this function is between these two functions, and the limit as x approaches a for f of x is equal to the limit as x approaches a of h of x equal to some limit L, then the limit as x approaches a of g of x must also be equal to L. That is the squeeze theorem, and that's basically what we proved when we found the area of that pizza slice. Or determined that the area of that pizza slice was between the area of that red triangle and the area of that blue triangle. Okay. Make sure you watch this video as much as you need to. And yeah, I hope this is helpful. Make sure you subscribe to this YouTube channel and like and share, all that kind of good stuff. See you guys next time.